Okay, continuing in an empty room because the battery on the camera died. We were doing some examples, or we were about to do some examples after having just learned the product rule. So let's just do that very quickly. There is the example that I opened the class with, x squared sine x, and maybe we'll do one more example. What is the derivative of, for example, I don't know, e to the x times x cubed. Okay, so these are both functions which can be thought of as the product of simpler functions which I know how to differentiate. So the product rule tells me that the derivative of the product of two functions is the derivative of the first times the second plus the first function times the derivative of the second. Bam. So that makes it, well, it's really easy to memorize and it's pretty easy to execute as well. You probably should just try this on your own really fast before I hit pause and finish this one and do the next one too. I'll just go really fast. The derivative of x squared is 2x, and the derivative of, and then just times sine. And then then we have x squared times the derivative of sine, which is cosine. So that's it. Next one, same thing. What is the derivative of e to the x x cubed? Well, it's the derivative of the first. The derivative of e to the x is e to the x times the second. Derivative of the first times the second plus the first times the derivative of the second, which is 3x squared. And then this one we can sort of factor nicely. I guess I can take out an x squared e to the x, and I'm left with x plus 3. So that's how to differentiate that. Okay, cool. I now know I have now suddenly vastly increased the number of functions which I can differentiate. And what I'd like to do is, if I've seen the derivative of a product, I would now like to come up with the derivative of a quotient. All right, so I would like to derive the so-called quotient rule. And the quotient rule says, well, what happens when you differentiate the quotient of two functions, assuming that I already know the derivative rules for each of them? Well, the initial thought might be, man, maybe I should do this using the definition of the derivative. Maybe I should do some gigantic derivation all over again. But no, I don't even really believe in division. Dividing is just multiplying by the reciprocal. And so the derivative of the f over g function is just the derivative of f, or is just the derivative of f times the 1 over g function. All right, so I can now apply the product rule to this. And the product rule says that this is going to be the derivative of the first, so f prime, times the second function, plus the first times the derivative of the second. All right, the problem is I have no obvious way to differentiate the 1 over g function. And so I'm going to pause this derivation of the quotient rule, and I am going to derive the reciprocal rule. And the reciprocal rule is another rule that most math teachers skip. It's not that famous. It's not in our textbook. But it describes how, in general, to differentiate the reciprocal of a function. Assuming I already know how to differentiate that function. Well, how do I do this? I guess we just try it. So just using the definition of the derivative, please take a moment, pause or whatever, but please do it yourself. Write out what the derivative of 1 over g should be using the definition of the derivative. Please pause and actually try it yourself. And then I'm going to do it right now. Well, okay, it is, the limit as h goes to 0 of this function evaluated at x plus h, so that's 1 over g of x plus h, minus 1 over g of x, and that's all over h. All right. Instinct tells me that I should try to clean this up a little bit, so let's do a little bit of algebra, get a common denominator. All right, skipping some steps, being sort of sophisticated, this turns into g of x minus g of x plus h all over g of x plus h, h. All right, and after staring at this for a few minutes, I play a little game of spot patterns and see what's going on. Well, I kind of notice here that this stuff here in the red loop, oops, I missed the H. This stuff here in the red loop kind of looks a lot like the derivative of g. In fact, it's almost exactly the derivative of g, except we're off by a negative. So in order to evaluate this limit, it suggests that I should try to like split this up in some kind of way. So if I do that, let me both split up the limit and also factor out a negative. If I do that, I get negative the limit as h goes to 0 of g of x plus h minus g of x all over h. That's the first limit. And then what I have here is everything that's left over. The limit as h goes to 0 of, well, I guess it's 1 over g of x plus h. And this is a totally legitimate move, provided both of these limits exist, and they just do. Because this is, well, by the definition of the derivative, this is just g prime. And this, as h goes to 0, I just get 2 copies of g. So this is times 1 over g of x, g of x. Okay, this is awesome. I have this new rule called the reciprocal rule. And the reciprocal rule says the derivative of the reciprocal of a function is the opposite of the derivative of that function all over that function squared. All right, and this is kind of a cool rule which people don't teach, but they should, because it immediately enables me to come up with a couple of derivatives which I might otherwise not have known how to do. So some more examples over here. Examples. Let's take what's the most obvious function which I typically think of as the reciprocal of some other function? Something like secant. So what is the derivative of secant that has been missing from our world so far? Now I can do it. Because I simply think of secant as 1 over cosine, and as cosine is a function I know how to differentiate, then I can apply the reciprocal rule. All right, let's do it. The reciprocal rule tells me that the derivative of 1 over something is going to be the opposite of the derivative of that something, and the derivative of cosine is a negative sign, over that something squared. So we get cosine squared. Bam, just like that. Our answer is sine x over cosine squared x. And most people, instead of writing like that, because, you know, lines in your textbook are valuable, so if we hate fractions, we can rewrite this as tan x secant x. And that is how you will see the formula most often done. And what you should do right now is pause the video and derive the formula for cosecant x, also using the reciprocal rule. I'll let you do that yourself. In fact, I think we'll just move on. And by moving on, I mean move backwards. And now that I have conveniently derived this reciprocal rule, I'm ready to finish my derivation of the quotient rule. So let's do it. What do I have here? I have f prime of x over g of x plus f of x times, and now I just know what this is, right? And the answer is it's negative g prime of x over g of x squared. And this is looking very tempting to get a common denominator here, And when I do so by multiplying the top and bottom by g of x, I get f prime of x, g of x, minus f of x, g prime of x, all over g of x squared. And this is the famous quotient rule. It says that the derivative of the quotient of two functions is the derivative of the first times the second minus the first times the derivative of the second. And now the situation is not symmetric anymore, so you do need to make sure you don't mess that up. All right, awesome. I'm gonna do two more quick things. This is terrible camera work, I'm sorry. We will just do maybe like two more examples. Let's see. There was this example. Let's do two more. Let's do something like, oh, here's a good one. What is the derivative of cosine x over x cubed? That's kind of a good one, I guess, maybe. And let's do what is the derivative of tan x. Also pretty exciting. And you should try both of these on your own by pausing and just doing it right now, and then unpause when you're done and check and see if you've got exactly what I got. I'll trust you to do that. All right, quotient rule says that this is going to be the derivative of the first. Derivative of cosine is negative sine. Derivative of the first times the second minus the first times the derivative of the second. I guess it's not really second anymore. It's derivative of the top times the bottom minus top times the derivative of the bottom. And that's 3x squared. And that's all over the bottom squared. So that's going to be x to the sixth. And in this case, it's possible for me to clean this up a little bit by dividing the top and bottom by x squared. And so what I actually end up with is something like negative x sine x plus 3 cosine x over x to the fourth. I think I did that correctly. Boom, boom. Took out the negative, there's a 3 involved. Pretty sure that's right. Yeah, cool. Okay, how about tan? Well, of course, tan can be represented as sine over cosine. And so what is the derivative of sine over cosine? Well, the derivative of sine is, well, okay, following the quotient rule, it's the derivative of the top, which is cosine, times the bottom, so that's another cosine, minus the top, which is sine, times the derivative of the bottom. And the derivative of the bottom is negative sine. And all of that is over the bottom squared. Okay, but of course, if you're experienced with trigonometry, you see that this is just cosine squared x plus sine squared x over cosine squared x, and that top becomes just 1. So our final answer is 1 over cosine squared, or as it is reasonably put, secant squared. All right, this is just awesome. I don't even know what to say. Suddenly, I just feel the power that I can do anything. I can differentiate cosecant, I can differentiate secant tan. Of course, you can do cotan, and should right now, because that's a rule that you need to know. And either memorize or be able to rederive very quickly, as I've done here. Is there anything else I wanted to do? Of course there is. Oh yeah. Not sure if I'm in frame or not, but let's do this. 9x cubed minus 5x squared minus 1 over root x. Okay, this seems like a perfect application of the quotient rule, and if I was doing this normally in class, I would give everybody 2 minutes and watch them trying to apply the quotient rule here, which is quite annoying. But part of using the quotient rule is knowing when not to use the quotient rule. And this
And the answer is I should not use the quotient rule as often as possible, right? So in other words, don't use the quotient rule unless you have to. And here we just don't have to. This is an example in which if I just simplify my function prior to differentiating, everything is like way better. By exponent rules, this is really just 9x to the 5 halves minus 5x to the 3 halves minus x to the negative 1/2. Hopefully I did that correctly. I believe I did. And now, by using the power rule, specifically the power rule for fractional exponents, which I haven't proved yet, but will soon, this is going to be, bring down the power, I guess that's 45 halves x to the 3 halves minus 15 halves x to the 1/2. And then that's going to be a plus 1/2 x to the negative 3 halves. All right, so relatively sophisticated and advanced algebra exponent skills are required in this subject as well. All right, last thing, which I've never done before in class, but I learned recently, the product rule is so awesome that it in fact can be used to derive the power rule. Okay, how does that work? Well, if someone asks me to differentiate x squared, and I have not, and recall that we did this, well, we did it 2 ways. We did it, first you could just do this using the definition of the derivative, and it's quite simple limit. Alternatively, you could do the power rule in general, of which this is a particular case, and the power rule in general depended on either using the binomial theorem, or this other thing we did with factoring a polynomial using the factor theorem. But instead, we could just think of this as x times x. And I know how to differentiate x. That can be shown by brute force, that the derivative of x is just 1, using the definition of the derivative. And so what do we have here? We have the derivative of the first, 1, times the second, plus the first, x, times the derivative of the second, 1. Bam, 2x. It's like amazing. In fact, what we'll do right now is just prove the power rule by induction. Okay, so claim that the derivative of x to the n is nx to the n minus 1. Okay, so what is our base case? Well, I guess our base case is when n is, can I just do 1? Yeah, I think I can just do 1. Base case, n equals 1. Right? Yeah. So according to the base case, well, what is the derivative of x to the 1? Oh yeah, I guess it's just 1. Which I suppose I've shown that via a limit. I'm going to skip that right now. You can do that yourself. Well, according to the formula, the derivative of x should be, x to the 1 should be 1x to the 0, which is 1. So everything works and the base case is complete. I'm being slightly fast about this. Okay, and now we make our inductive hypothesis. And our inductive hypothesis is that it's true for a particular n. Or I guess we'll do it with k's, because why not? So our inductive hypothesis says that, so we're going to suppose that the derivative of x to the k is kx to the k minus 1 for some k greater than or equal to 1. And then what I need to prove in order to complete the inductive step is on this assumption that the derivative of x to the k plus 1 is k plus 1 x to the k. All right, assuming you're with me, now we'll just do it. All right, so here comes the proof. We will take the derivative of x to the k plus 1, and we will hope to show that it is indeed that. And I will use just the power rule. And the power rule says that the derivative of x to the k plus 1, well, it's the same thing as, if I rewrite x to the k plus 1 as x times x to the k, then this is going to be the derivative of the first, which is 1, times the second, x to the k, plus the first, x, times the derivative of the second. And the derivative of the second is kx to the k minus 1. Alright, so what we have here is x to the k, and what we have here is k times, well, x times x to the k minus 1 is just x to the k. And this is, if I factor out an x to the k, this is just k plus 1. So k plus 1 x to the k. As required. Awesome! And now, let's see, I'll throw in the magic sentence. The magic sentence is, since the derivative of x to the 1, actually I don't feel like writing out the magic sentence. That completes our video, or that completes our lecture number 10. We now know how to differentiate polynomials. Constant times functions, sums of functions, products of functions, reciprocals of functions, quotients of functions. That we know how to do sine, cosine, all the other trig functions. We know how to do e to the x. There's many, many, many functions which we now know how to differentiate, but there are still some that we do not know how to differentiate, and that is coming up next class. Okay, great. This concludes lecture 10. I'll see you all later.